P-type will be connected to positive terminal of cell and N-type will be connected to negative terminal. I'll forward bias it. Okay, let's go back to the structure. Can you remember the energy band diagram? So there's a valence band, there's a conduction band. There'll be some free electrons will be there, no? Due to thermal agitation, and equally those many number of holes will be there. And these free electrons, they need not be at same level. They can be at different levels. Okay, that's the thing. And this energy gap for ordinary semiconductors, how much this energy gap will be? For ordinary semiconductors, how much it is? 1 electron volt, no? So let's say that 1 electron volt. Now, as I forward bias, I'll increase the bias. I'll increase the bias. As I increase the bias, what actually happens here is the most energetic, without bias, the most energetic electron is able to cross the depletion layer from N to P type. The most energetic hole is able to cross from P to N type. Most energetic only, not all holes. Most energetic hole is able to cross from P to N type. What about other electrons? Their energy may not be sufficient to cross our depletion layer. Similarly, what will happen to the holes here? Let's come for holes. Holes are minority carriers. So these what will happen? Battery is a negative terminal due to thermal agitation. By chance, if the hole comes here, what this depletion layer will do? Will pull it towards P, no? So therefore, the flow of minority carrier will be like this. Similarly, there's a minority carrier. So what depletion will permit? It will permit the flow of minority carrier. So we have like this a diffusion current, and this is a drift current. And without any bias, so what happened to diffusion and drift current will be equal and opposite. Okay, and we have some thermal agitation, covalent bonds will break up, all that is there. So in LED, it will also take place. I'm not much interested. No, let's come for this one. How there's a flow of electron. Almost today now, what all I discussed, 3 devices, no, the same explanation. So therefore, that's why I have put more effort in the PN junction. The same explanation you have to take help of this one. Okay, there's a free electron. So what this battery does, it will inject electrons. Prior to bias, the most energetic electrons were able to cross from N to P type. Now, as I increase the bias, what happen? Along with this most energetic, what happen? The other electrons also are able to cross over, no? And these electrons, the freshly injected, few they will cross over along with the most energetic. And some electrons here, what happen? They'll get support from the cell. They'll also cross over. So what will happen to a number of electrons moving from N to P type? With bias, without bias. With bias will be more than without bias. I think everyone will agree this. Then these electrons, when they're flowing open, they'll occupy some place here, no? And similarly, the like here, this electron will occupy this. Instead of crossing over like this, it may occupy this position. So what will happen to width of depletion layer? Decreases. Let's talk about this electron. So as let it crosses here. The moment it arrives here, how do it will move? It will move like a valence electron. It will be captured by hole. We'll get a valence electron. Then it will jump like this, no? And it will come out. So what this positive terminal will do? It will pull out valence electrons from here. It will pull out valence electrons here. So like this what happen, the all what will happen, and this all what happen will pull out. Better say like it, this all will pull out valence electron from here. This all will pull valence electron. This valence electron will be pulled by the cell. Get this? So width of depletion layer decreases. Okay, I'm more bothered about this carriers, majority carriers. The majority carriers by the time like a all moves from P to N type, what will happen to them? They'll undergo recombination. Similarly, the majority carriers like a N electrons from N type, when they cross from N to P type, they'll undergo recombination here. So what will happen to this electron? Some electrons will successfully cross over it and they'll undergo recombination. Some electrons, while crossing what happen, they'll occupy this position. And some electrons what happen will undergo recombination here only. Will be captured by the vacancy. It is, I think I shown. Covalent bonds will break up, no? And due to breaking up of covalent bond, all will move like this. And the electron, okay, there's a minority carrier current, no? And it will be like this. Anywhere, I'll show it here. It's a minority carrier, no? Arrows also I will indicate, so that will be easy for you. All will contribute the drift current, the blue color lines. All will contribute for the diffusion current. This one, okay, we'll show it till here. This I'll show it till here. Okay, fine. You can start thinking here. It will not. It should take somewhere position here, no. That, and this electron can go till here only. I think I am able to give very good explanation, because who will fill up that breaking and making up? Who will fill up that broken the covalent bond? This electron. So all these are the things. Let's not bother. So these are about things. Okay, now I'm primary. Let's get into the primary aspect. What is that? The electrons from when they cross from N to P type, what will happen to them? They'll undergo recombination. Finish work. Yeah, it'll be captured by hole. So when an electron, when an hole captures a free electron, what do we get? We get a valence electron plus photon. This photon, why the photon? Okay, let's come for this one. When a free electron makes a jump from conduction band to valence band, go back to hydrogen, go back to the hydrogen, go back to the hydrogen. So when an electron makes a transition from higher orbit to lower orbit, it should give out a photon, no? Here it gives a photon lambda. Similarly, an electron can make a transition from here, no? Look at lambda 1, lambda 2, must be same or different. Depends on energy level, no? To make it problem very, you can select a simple. I'm just showing the transition from different levels. In conduction band only, not one line. It discrete energy levels only will make a conduction band, no? Lambda 4. Okay, I think you have everything. Yeah, that one. This particular lambda. So for ordinary semiconductors, this will be given out as heat, will be absorbed, will be converted into heat. The photon that is being generated due to recombination of majority carriers, they'll be converted as heat for ordinary diodes. Why heat? Because the material will not permit that particular photon to come out of material. So who is that? For silicon and germanium, what they do, they'll convert this particular photon energy in the form of heat here. And in what visible spectrum it is? So let's calculate the some energy thing. Lambda equal to SC by E. So this, let me take 1, 2. Energy is 1 electron volt. No? So look at the range. We'll get in Armstrongs, this one. So 12,400 Armstrongs. Okay, well, look at the, is it in visible spectrum? Energy band gap for germanium silicon. This is for germanium and silicon. What all that wavelength that is available due to recombination will be of order wavelength 12,400. Visible spectrum how much? 4,000 to 7,000 Armstrongs. So what happened to this particular photon will be absorbed by the material. So for ordinary diodes, means what? Germanium and silicon. The photon generated due to recombination will be absorbed by material itself. Any reason for that? First, there's the first. Second reason, germanium silicon. Why don't this particular photons come out of material? They are opaque. Germanium and silicon, all of you opaque. Will they permit the light to pass through it? No. Germanium silicon or opaque substance. Due to will be absorbed by the material and they'll eat up. Will be converted as heat. This is what happens in germanium silicon. So I'm not bothered. Let them get eat up. That's why if you see mobile, when you start using it for 1, 2, 3 hours, I think after 2 hours you can't even touch your mobile. No, why it has become heat? Because of this thing. Because of this lambda. If you take the laptop, there'll be cooling fans will be there. Am I right? You can see beside there'll be a cooling fan will be there. So the heat will be taken out. This is what happens for ordinary diode. So let's come for the germanium. Like I want this to be in visible spectrum and it should be visible. Light emitting diode. I want a diode when it's forward bias should emit light. It should emit light means what should be the wavelength? 4,000 to 7,000 Armstrong units. Okay, let's check the lambda 1. First lambda 1 SC by E1. So what should be the energy gap so that lambda should come? So I'll bring it. Okay, anybody, can you give the value? Anybody value of that?
3.1.
3.1, no? 3.1 electron volt. Now similarly, 7,000 approximately. Just give the value. One point seven. So what should be the band gap? The band gap should be like this. Huh? So, but germanium silicon, what is the band gap? We know it is 1 electron volt, no? Approximately. So, but I want a, when a diode is forward biased, instead of each generated voltmeter, it should be converted into light. So for that, what I should do, I should adjust a band gap. So from where to bring that material? Yes, we do have material. Where what happen for the band gaps will come. I can bring the band gap. I want infrared. I want ultraviolet. I want even the so like a different colors. So for that purpose, what happen? I'll adjust the band gap. How to adjust band gap? By going for the combination of materials. I will introduce the tabular column. I think this will semiconductor material wavelength emitted in Armstrongs, possible color, and the forward voltage. This one. So gallium arsenide is one material. 8,500 to 9,400. This is the wavelength. And it will lie in the spectrum. Infrared and forward voltage is 1.2 volt. Gallium arsenide for it's also compound semiconductor material. These are 6,300 to 6,600. This will be red. Forward voltage is 1.8 volt. Gallium I think some more. This is called as amber. 2 volt it is. Gallium arsenide, phosphide nitrogen. All these are aluminium gallium phosphide. 5,500. 5,700. This will be, I think, yeah, green color. 3.5 volt, 2 volt. Let me silicon, carbon. This will be the blue. Gallium. If this semiconductor made up of semiconductor, you forget germanium silicon. Gallium arsenide is called as compound semiconductor materials. What are these are? Compound semiconductors. Gallium arsenide. I'll make a diode using gallium arsenide. Same thing. I'll dope it everything. Then then when I forward bias, then there what will happen? I'll get a photons recombination will occur. Recombination of majority carriers will occur. Then the photon will be of this particular wavelength. Then if I check it, no, it lies in infrared. What is the forward voltage? 1.2 volt. If I make the material using gallium arsenide phosphide, semiconductor material, then I'll dope it p-type, n-type, I'll forward bias it. Then when majority carriers undergo recombination, when they cross from across the depletion layer, when I cross over the depletion layer, then we'll get red color. This will be around, say, like a 1.8 volt, the forward voltage. And what is the thing? All these compound semiconductors. What are the things? What are the features of compound semiconductors? First feature, what should be? Transparent. Material should be transparent. Material must be transparent. Okay, fine. There's a four more feature. Next again. should be in crystalline form, can be doped. These are the basic features. Huh? Metal must be transparent. There's a foremost condition. Transparent means what? It should permit the EM wave to pass through it. Ordinary diode will not permit, so opaque, but metal must be transparent. Then only the light will come out of the diode when it's forward by. The light should come out of the diode when it's forward by rear. All these materials are transparent for the light. For infrared, everything this is. So we'll get here what happen when forward bias, the diode starts emitting light here. Means what we have to show, come back here. Let's say it's made up of gallium arsenide. Now due to recombination occurs, no? From here what happen, we will get a light. The diode starts emitting light. Now what are these arrows? You show like this. What is the green color arrow? This is a light. From where this light is coming? Due to recombination. I think now you have mobile, no? Just switch off their white LED. Of course, we don't have anything white LED. I will go for the combination. Later on in the end, I'll tell you that one. So I think you have in mobile, no? The LED will be there. So how it has come? It's not a bulb, it's LED. That I think now in home we have LED bulbs, no? White LEDs is what are more popular. But if you go for application mobile, I think you have some red blink will come, blue blink will come. Everywhere we are using now. So how do that red color LED will come? I just make semiconductor material. If it is made up of different materials, or mean having the different band gap. For different band gap, the wavelength emitted will be different. For different wavelength, different colors will get it. And next what I do, I'll go for combination. I'll go for combination of all. How do I get white light? For white light, we don't have separate material. For white light, we don't have separate material. So what we do is yellow and the blue will be combined. If I combine yellow and blue, what will happen? We get the white light. This is the best method available for us. I'll show it. Blue, I think. Yeah, this one only. When we combine like this, we'll get white light. Huh? Okay, let's not bother mixing of colors. Huh? So let's take it for this one. So there's a one idea. So here is what? White. This is yellow. And this is blue. So like that, what when there's a material, of course, I use by combination of that one will go for it. So what I do is like first yellow to be gallium arsenide phosphide. How do that? Because everyone will be more curious. There's a material first gallium arsenide phosphide. This will be yellow color material. So this one gallium arsenide phosphide. Then I will surround it by due to superposition of these two open, we'll get a white light. What is this material? This material is blue, no? Silicon carbon. So what we get here outside what happened, the superposition of these two will give white light. Okay, I think let's not bother with the construction of that one. Huh? It's of no use because we have to go again in deep more. Like this, by going for again combinations, I'll get a different colors light. Like this, I think you can see some, for a god photo, we'll get a blinking LEDs, different colors will come. We'll go for combinations of that. So now what is the basic idea? What is the overall theory? For ordinary diode, due to recombination, what all that photon will be given out will be converted as heat. The reason for that, the germanium silicon are opaque substance, and what all the wavelength that is given will be of order 12,400 Armstrongs, and will be converted as, will be absorbed as heat. Now instead of germanium silicon, I will make materials like this. Then I'll dope it p-type, n-type, then I'll forward bias. Then due to when the recombination occurs, the photon given out will be of range like this for different materials. So different applications, I'll go for different materials and I'll get the different colored LEDs. That one given LED cannot give multiple colors. I'm making things clear. Gallium arsenide infrared, I think will not visible, no. Gallium arsenide phosphide red, gallium arsenide phosphide, some changes I'll make it, I'll get amber, then this will be yellow. Like that we'll get a different, for different material different colors. And look at the band gap. Now there's a forward voltage. What's with the band gap? I think now you know wavelength, calculate the band gap. So by varying the band gap of semiconductor material, we can make it to emit different colors light. This is a basic idea. Agree this? Okay, let's come for the what will be the, okay, a given LED, it's emit light. Will it be monochromatic? Look at this transition. All electrons will not be in one state, no? And moreover, I'll bring another state. No, who are these electrons? Why these electrons are there? Why these electrons? I think they'll also come into picture, no? They'll also start emitting light. I'll give a better diagram. Huh? So many arrows. We'll go for few arrows only. We'll go for simplified diagram. Now, what are there's a valence band. There's a conduction band. Then we have, there's a PN junction diode, no, here. So here free electrons and we'll get a holes. You can show a number of electrons and holes that should be equal. Huh? That number I think I may miss out. How many other 8 and 8? Okay, fine. What are the transition? The transition can take place like this. Let's show only few arrows, huh? And it can undergo transition till here. This can undergo transition here. Conduction band to, like till here it can undergo transition from conduction band to valence band. This is the one thing I'm showing. Then again from conduction band to the acceptor level. Even it can happen like this. Okay, what are the possible? The electron can jump from conduction band to donor level. Electron can jump from conduction band to acceptor level. Electron can jump from conduction band to valence band. Okay, fine, possibility. Then electron can make a transition from where? From donor level to acceptor level, or from donor level to the valence band. So like this, when you forward bias a diode, what are the possibilities? These are 5 possibilities are there. So what is this? I didn't understood this. So I think this electron, when it is moving, it may capture here, no? It may come till here. Or this electron, what pen? This electron you see will cross over, will come to this, will be captured by hole. Okay, and there can be all what happen at the donor level or in the valence band, no? The holes. So this is a thermal. So like this, what happen? So these are possibilities are there. So tell me now with this, when you forward by say LED, will it be monochromatic? That's what my question. The answer is not monochromatic. Monochromatic means what happen? The transition should take place from one level to other level only. But you have look at the energy levels are different here. Of course, this energy level will be different, but still what happen? If you compare this wavelength and this wavelength will be different. No, if you compare this wavelength and this wavelength will be different. So therefore, LED will emit monochromatic light. The answer is no. So sir, how the spectrum will be then? So either you take yellow, will you get only one wavelength? Are you able to understand why we have to show this range? Because of transition like this. Are able to catch? I think in books they didn't stress much here, but LED will not emit monochromatic light. That's what I mean to say. That's why I gave the range. Why this range will come? Because of the transition. Because the electron can make a transition from conduction band to donor level, conduction band to acceptor level, conduction band to valence band, or from donor level to acceptor level, donor level to valence band. Any of the possibility, or all from I'm speaking about only electron, but even the all can make transition to here or to here, or even this electron from here can come till here. So therefore, if I plot the graph like this, intensity versus wavelength. What is this? Intensity of any color, you can take it, watt per meter square, not current, it is the intensity. Then how the curve will be? The different photons emitted will not have different, means the different photons will have different wavelength here. And what about their number? So this will be some peak. There are some photons or depend, they'll have more, they're more energetic. What about the number? Less. Again, don't show like this. Huh? Don't show like this. Don't show like this. This much of broad, it will not be there. Because you can see that 4,300 to 550. It is so very small difference of 200, 300. The difference will come. Okay, this will be the spectrum. In books are not there possibility of asking. Huh? You have to be careful. This is intensity. So the light emitted by LED is not monochromatic. So what LED does, it will, shall I say, it will convert electrical energy into light energy. It will convert electrical energy into light energy. That's all. It will convert electrical, ordinary diode, it will convert electrical energy into heat energy. What about LED? Converts electrical energy into the light energy. Okay, next one more point. So just I'll keep on had the data. You have to just remember nothing else there, because you can see that you need not to put any much effort here. Now, what is LED? Converts electrical energy into light energy. Light emitting diode. This is the thing. Okay, let's go for the other parameters.